Hi, welcome back to my class in Advanced Statistics. For today, we will take up the empirical rule, and this is very similar to the Chebyshev's theorem. In Chebyshev's theorem, we said that for a positive integer k greater than equal to 1, at least 1 minus 1 over k squared of the set of measurements or distribution of measurements lie within k standard deviations from the mean. To recall that Chebyshev's theorem states that for a positive integer k greater than equal to 1, at least 1 minus 1 over k squared of the set of measurements lie in the interval from mu minus k sigma to mu plus k sigma, or at least 1 minus 1 over k squared for k greater than equal to 1 are contained in the interval mu plus or minus k squared, that is at least 1 minus 1 over k squared, lie within k standard deviations from the mean. Mu minus k sigma is k standard deviations to the left of the mean, while mu plus k sigma is a point that is k standard deviations to the right of the mean mu. In using the Chebyshev's theorem, we must be given the population mean or the expected value of the discrete random variable x, as well as the standard deviation of the discrete random variable x. Now, if in particular k is equal to 2, if we take a particular value of k, say k is 2, 1 minus k squared becomes 1 minus 1 over 2 squared, which is equal to 3/4, or in percent, 3/4 is 75%. By Chebyshev's theorem, this means that at least 75% of the set of distributions of measurements or values of the discrete random variable x lie between mu minus 2 sigma and mu plus 2 sigma. That is, at least 75% of the set of measurements lie within 2 standard deviations from the mean. Mu minus 2 sigma is a point that is k standard deviations to the left of the mean, where the mean mu is located at the center of the distribution of measurements, while the point mu plus 2 sigma is a point that is k standard deviations to the right of the mean. If k is equal to 3, then we have if we take another value of k, say k equals 3, then 1 minus 1 over k squared becomes 1 minus 1 over 3 squared, which simplifies to 8 over 9. And 8 over 9 in percentage to 2 decimal places is 88.89%. By Chebyshev's theorem, this means that at least 88.89% of the set of measurements are contained in the interval from mu minus 3 sigma to mu plus 3 sigma. That is at least 88.89% or 8 over 9 of the set of measurements lie within 3 k standard deviations from the mean. Mu minus 3 sigma is a point that is 3 standard deviations to the left of the mean. While this right end point of this open interval, the point mu plus 3 sigma, is a point that is 3 standard deviations to the right of the mean. Now, the empirical rule is more specific because it applies most especially for distribution of measurements that is normal. Now, we state the empirical rule. To state the empirical rule, in the empirical rule, the given distribution of measurements is normal or approximately normal, and we should know the values of the mean, population mean, or the expected value of the discrete random variable x, as well as the standard deviation of the discrete random variable x. According to the empirical rule, 68% of the measurements are contained in the interval mu plus or minus 1 sigma. That is, in a normal distribution of measurements, 68% of the measurements lie within 1 standard deviation from the mean. The empirical rule also says that 95% of the measurements in a normal distribution of measurements are contained in the interval mu plus or minus 2 sigma. That is, 95% of the measurements in a normal distribution of measurements are contained lie within 2 standard deviations from the mean. And finally, 100% or almost all of the measurements in a normal distribution of measurements are contained in the interval mu plus or minus 3 sigma. That is, 100% or almost 100% of the measurements in a normal distribution of measurements lie within 3 standard deviations from the mean. The main difference between the empirical rule and the Chebyshev's theorem is that The empirical rule applies for a normal distribution of data, while the Chebyshev's theorem applies for distribution of measurements that is mound-shaped or skewed either to the right or to the left. However, the empirical rule applies for distribution of measurements that is not bell-shaped or normal as well. Now we take examples to apply the empirical rule. For our first example, we consider the following problem. A time study is conducted to determine the length of time necessary to perform a specific operation in a manufacturing plant. The length of time necessary to complete the operation is measured for each of n equals 40 workers. And here is the sample size, n equals 40 workers. The mean and standard deviation are found to be 12.8 and 1.7 respectively. The units of time are not given. Describe the sample data by using the empirical rule. The only things that we need in applying the empirical rule are the mean, denoted by mu, and in this particular example, the mean mu is equal to 12.8. And we also need the standard deviation. For this particular example, we are given that the standard deviation is 1.7, denoted by the Greek letter sigma. And by empirical rule, it says that 68% of the measurements for each of the 40 workers lie in the interval mu plus or minus sigma. Or this open interval is equivalent to the open interval with left endpoint mu minus sigma and right endpoint mu plus sigma. And we compute this value mu minus sigma. Mu is 12.8 minus 1.7. We also compute the right endpoint mu plus sigma, where mu is 12.8 and sigma is 1.7. And we use a calculator to compute 12.8 minus 1.7. And that's 11.1. The right endpoint is 12.8 plus 1.7. 12.8 plus 1.7. And the calculator gives us 14.5. By empirical rule, it means that 68% of the 40 observations, because for each test, we have a sample of 40 workers, and they work on a certain operation to determine their completion time for that specific operation. And out of these 40 workers, their completion times, 68% of the 40 workers, or 68% of the completion times, that is 68% of 40 is 0.68 multiplied by 40 equals 27.2, or 27 of the workers have completion times in performing this specific operation between 11.1 and 14.5. We do not know the unit of time. Out of 40 workers who perform the operation, approximately 27 or 68% of the 40 workers have completion times that are between 11.1 and 14.5 units of time. The empirical rule also says that 95% of the distribution of measurements lie in the interval from mu minus 2 sigma and mu plus 2 sigma. According to the empirical rule, 95% of the observations or distribution of measurements lie in the interval mu plus or minus 2 sigma. That is 95% of the observations or measurements lie within 2 standard deviations from the mean. And this interval is equivalent to this open interval with left endpoint mu minus 2 sigma and right endpoint mu plus 2 sigma. And we compute these endpoints of this interval where mu is 12.8 and sigma is 1.7. Mu minus 2 times sigma is 12.8 minus 2 times sigma 1.7. Mu plus 2 sigma is 12.8 plus 2 times sigma 1.7. And we compute this using our calculator. We have 12.8 minus 2 multiplied by 1.7. And we get 9.4. The right endpoint we compute 12.8 plus 2 times 1.7 using calculator. We have 12.8 plus 2 times 1.7 and we get 16.2. The empirical rule says that 95% of the observations or measurements lie in the interval 9.4 to 16.2. That is 95% of 40 because we have 40 workers for each trial. And 95% of 40 is 38. That is 38 workers have completion times in performing that specific operation that lie between 9.4 and 16.2 units of time. Again, by empirical rule, 68% of the observations, 68% of 40, that is 40 workers who work on an operation and their completion times were recorded, and 68% of 40 or approximately 27 of those completion times lie between 11.1 and 14.5 units of time. And 95% of the measurements, specifically 95% of 40 or 38, workers who have completion times that lie between 9.4 and 16.2 units of time. In Chebyshev's theorem, this interval 11.1 to 14.5 would contain 3/4 or 75% of the measurements. That is, 75% of 40 have completion times that lie between 11.1 and 14.5 units of time. Also, for the interval mu plus or minus 2 sigma, if you are using the Chebyshev's theorem, it says that 8/9 or 88.89% of the measurements, or 88.89% of 40, are contained in the interval 9.4 and 16.2 units of time. And finally, the empirical rule says that 100% or almost 100% of the measurements are contained in the interval mu plus or minus 3 sigma. The empirical rule says that 100% or almost 100% of the measurements or observations are contained in the interval mu plus or minus 3 sigma, or 100% of the observations lie within 3 standard deviations from the mean. And this interval is equivalent to this open interval with left endpoint mu minus 3 sigma and right endpoint mu plus 3 sigma. And we compute the left and the right endpoint by substituting mu equals 12.8 and by substituting the value of sigma equals 1.7. The left endpoint is 12.8 minus 3 times 1.7, which we compute using our calculator. We have 12.8 minus 3 times 1.7. We get 7.7. We also compute using calculator 12.8 plus 3 times 1.7. And our calculator gives us 17.9. Now, this open interval from 1.7 to 7.7 to 17.9 means that 100% or almost all of 40 workers have completion times that lie between 7.7 and 17.9 units of time. And that's according to the empirical rule. Now we take another example for applying the Chebyshev's and empirical rule. For our second example, consider the following problem. The extent of a firm's involvement in a new product research depends on the industries in which the firm competes. A survey was made of firms in high technology fields to find the number of new products each firm introduced during 2019. From the survey, the probability distribution for the number of new products introduced by each high technology firm during 2019, X is shown below. Find the expected value and variance or variance of X. Give the proportion of high technology firms for which X exceeds mu plus 2 sigma. In this particular problem, the discrete random variable X is defined to represent the number of new products that each high technology firm introduced during the year 2019. And the possible values of X are 3, 4, 5, 6, 7, 8, 9. That is, 3 products were introduced by each high technology firm during the year 2019, or 4 new products were introduced by high technology firm during the year 2019, and so on up to 9. X equals 9 means that 9 new products were introduced by each of the high technology firms during the year 2019. And the corresponding probability for each value of the discrete random variable X is given by these values. The probability that 3 new products were introduced by a high technology firm is 0.08. The probability that 4 new products were introduced by a high technology firm during the year 2019 is 0.14. And so on up to 9. The probability that X equals 9 or 9 new products were introduced by a high technology firm during the year 2019 is 0.04. We start by finding the expected value of the discrete random variable X. The expected value of the discrete random variable X, denoted by mu or population mean mu, is obtained by using this formula, summation of X times the probability of X. Hence, to find the expected value of the discrete random variable X, or the mean mu, multiply each X by its corresponding probability and add the products. We have 3 multiplied by 0.08 plus 4 multiplied by 0.14. We use plus because the operation indicated by summation, or the sigma notation for summation, is addition. Plus 4 multiplied by 0.14 plus 5 multiplied by 0.22 plus 6 multiplied by 0.30 plus 7 multiplied by 0.14 plus 8 multiplied by 0.08 and plus 9 multiplied by 0.04. And we compute the sum of the products using our calculator. We have 3 multiplied by 0.08 plus 4 multiplied by 0.14 plus 5 multiplied by 0.22 plus 6 multiplied by 0.3 plus 7 multiplied by 0.14 plus 8 multiplied by 0.08 and finally plus 9 multiplied by 0.04. And you should get 5.68. This means that approximately 5.68 new products on the average were introduced by high technology firms during the year 2019. Now we compute the variance or variance of the discrete random variable x denoted by sigma squared. Variance or variance of a discrete random variable x is computed by using the following formula, and the variance or variance of discrete random variable x is denoted by the Greek letter sigma to the power 2 or sigma squared. And this formula and this variance or variance of discrete random variable x may also be computed by using this alternative formula, but we will use both of them so we can check our answer. We start by using this formula. We take the square of the difference between each value of x and the expected value of x and multiply that by the probability, the corresponding probability of x, and we add the products. So sigma squared using this formula is equal to the first value of x is 3 minus the expected value of x is 5.68 as we have computed earlier. Raised to the power 2 and multiply by the probability of x. The probability of 3 is 0.08. Plus, we use plus because the operation indicated by the sigma notation for summation is addition. Plus, the second value of x is 4 minus the expected value of x, 5.68. Raised to the power 2 and multiply by the probability of 4.14. The next value of x is 5 minus the expected value 5.68 raised to the power 2 and multiply by the probability of x equals 5.22. The next value of x is 6 minus the expected value of x is 5.68 raised to 2 multiplied by the probability of x equals 6.30. The next value of x is 7. 7 minus the expected value of x, 5.68, raised to the power 2 and multiply by the probability of x equals 7.14. The next value of x is 8 minus the expected value of x, 5.68, raised to the power 2, multiplied by the probability of x equals 8, which is 0.08. And the last term in the summation is for the last value of x, x equals 9, minus the expected value of x, 5.68, raised to the power 2, multiplied by the probability of x equals 9, 0.04. And we compute this using our calculator. We have 3 minus 5.68. We have 3 minus 5.68 square multiplied by 0.08 plus 4 minus 5.68 to the power 2 multiplied by 0.14 plus 5 minus 5.68 square multiplied by 0.22 plus 6 minus 5.68 square multiplied by 0.3 plus 7 minus 5.68 square multiplied by 0.14 plus 8 minus 5.68 square multiplied by 0.08 and finally plus 9 minus 5.68 square multiplied by 0.04. And to two decimal places, you should get 2.23. The answer in the calculator is this decimal number, but we round off the final answer to two decimal places. After the decimal point, you count 3, 1, 2, 3. The digit to be rounded up is 1, but 1 is less than 5. So we simply drop 1 and all the digits to the right of 1. And we get 2.23. Now we check if this answer is correct by computing the variance of x using this alternative formula for computing the variance or variance of the discrete random variable x. We take the square of each x and multiply the square by the probability of x. We start with the first value of x. X is 3. 3 square is 9. Multiplied by the probability of x, 0.08. Probability of x equals 3 is 0.08. plus, we use plus because the operation indicated by the sigma notation for summation is addition. The square of the second value of x is 4. 4 squared is 16. Multiplied by the probability of x equals 4 is 0.14. Plus the next value of x is 5, square it, 25, multiplied by the probability of x equals 5, 0.22. Plus the next value of x is 6, and square it, 36, multiplied by probability of x equals 6.3. Plus the square of the next value of x is 7, square is 49. 7 squared is 49, multiplied by the probability of x equals 7.14. The next value of x is 8, and we square it, 64, multiplied by the probability of x equals 8.08. And the last term is the square of the last value of x, which is 9. 9 squared is 81. Multiplied by the probability of x equals 9.04. Minus the square of the expected value of x, or the mu or mean of x, 5.68 minus 5.68 squared. And we compute this by using our calculator. We have 9 times 0.08 plus 16 times 0.14 plus 25 times 0.22 plus 36 times 0.3 plus 49 times 0.14 plus 64 times 0.08 plus 81 times 0.04 minus 5.68 squared. And we get 2.2176. Using our alternative formula for computing the variance or variance of discrete random variable x, we get 2.217, and to two decimal places, we round up 7. Since 7 is more than 5, we add 1 to the preceding digit 1, and we get 2.22. And you can see that there is a difference of 0.01, but if we round up the variance sigma squared to one decimal place, we would get the same value, 2.2, using this formula, and 2.2 using this alternative formula. For our computations, we would use the first value, 2.23. And we now answer the next question. Give the proportion of the measurements or values of x that exceeds mu plus 2 sigma. We compute mu plus 2 sigma, where mu is 5.68. plus 2, and we take sigma. As I said, we use the first value of sigma. Our sigma squared is 2.23, and sigma here is the square root of 2.23, the square root of sigma squared, or the square root of 2.23. And we compute 5.68 plus 2 times sigma, the square root of sigma squared, 2.23, using our calculator. We have 5.68 plus 2 multiplied by the square root of 2.23. And you should get, if you round off your answer in your calculator to 2 decimal places, you should get 8.67. Now, by inspection of this given probability distribution table for the discrete random variable x, you can see that the values of x are 3, 4, 5, 6, 7, 8, 9. And among these values of x, there is only one value of x, 9, that is more than or that exceeds 8.69. Only x equals 9 exceeds 8.69. And the probability that x is 9 is 0.04. Thus our answer is 0.04, or per percent. %, or specifically only one value of x equals 9 exceeds mu plus 2 sigma, which is equal to 8.67. And that completes our solution for our example 2. For your practice and assignment, please try the following exercises. Number 1, a set of n equals 100 measurements has a mean of 33 and a standard deviation of 2.5. Describe the distribution of measurements using A. Chebyshev's theorem, and B. the empirical rule. Number 2, let x be the number of calls that an investment counselor calls each client during a given week, and assume that x is described by the following probability distribution. Find letter A, expected value of x, letter B, variance or variance of x, and letter C, the proportion of values of x that exceeds mu plus sigma. In number 2, the random variable x represents the number of times that an investment counselor calls its client. And the possible values of the discrete random variable x is from 0 to 4. And the corresponding probability of each value of x is given by p of x. And in number 2, you are asked to find the expected value or mean of the discrete random variable x and the variance sigma squared of the discrete random variable x. For letter B, use both formulas for computing sigma squared or variance of the discrete random variable x, but for letter C, to find the proportion of x values that exceeds mu plus sigma, use the value you obtain for sigma squared using the first formula. And that completes our lesson for today. If you have questions about the lesson today, you ask your questions in the comments below. But don't forget to subscribe to my YouTube channel, Art Kalison, the channel of learning and leisure. You may also ask your friends, your classmates, neighbors, and relatives to subscribe to my YouTube channel, Art Kalison. so they may learn as well. Thank you for joining me in my class today in Advanced Statistics.